Evening. It gives me great pleasure to welcome you once again to this second talk in the 2018 Ihaka lecture series. My name is James Curran. I'm the current head of statistics, and again, it's fantastic to see you all here. It's a great synergy between computer science and statistics and some other faces and people that I don't recognize. I would also like to welcome those people who are listening remotely. So we have an audience, a national audience, and we have an international audience as well. So there are groups who are watching this live in Australia, good on you, and in England. So good morning to you, and welcome to this series. Tonight we have a fantastic homegrown speaker, Paul Morrell. Some of you may know him, some of you may not. Paul has an interesting background in terms of his academic history, in that he has undergraduate degrees in both computer science and statistics and an undergraduate degree in psychology. And those of you who have read Paul's blurb will know that mastery, or at least knowledge of all of these disciplines, is essential in order to understand the concepts and things that he's going to talk to us about tonight. Paul, of course, did his PhD with Ross Ihaka, so again, a nice relationship. I'm going to steal a joke from Paul here, and he likes to tell us that Ross taught him everything he knows, including how to dress. I would like to point out that the student has exceeded the master on this occasion because, unlike normal, Paul actually has shoes on and long pants. Paul did his PhD in statistical graphics, and he told me today that Ross actually dragged him kicking and screaming into the R project, but it is the R project that we strongly identify with him with today, and he is one of the members of the R Corps, a group of individuals who control the fate of the Western world and R. Paul has done a variety of things. He's been, so he's PhD here. He did a brief postdoc in Cambridge in the United Kingdom before returning to the University of Auckland. He's worked on a large number of things, packages in particular around R. I'm not going to list those. And he has two very successful textbooks. If I had to describe Paul's research, I would say if you think of Hadley Wickham as owning the grammar of graphics, then Paul owns the ontology of graphics. Paul is very interested in the structure and cataloguing of statistical graphical objects and their relationships to each other. And on that note, I will hand over to Paul for, I'm sure, what will be a very interesting talk. Thank you.
Okay, hopefully, my mic is live. Well, both my mics are live, hopefully. Thank you, James. Very generous. Right, got a lot to get through, so I'll just get on with it. I'm going to talk to you about some work I've recently done on accessibility in the sense of people who, well, particularly people who are blind or visually impaired, allowing them to use R, and colour. So that's why those two words are on there. I'm going to emphasise the journey rather than the destination in this talk, partly because the destination is a bit disappointing, as I said in the abstract. What I'm going to try and do is sort of reflect on why it's quite fun to work in statistical graphics and try and draw out some sort of wisdom about how to create statistical graphics software, which is mostly what I do in my research. Okay, now at this point you normally have an overview, you say what you're going to say before you say it, but that would give away the ending, so I'm not going to do that. I'm just going to go through the story, going to emphasize the journey, and if you want to understand what's going on, you just have to stay awake all the way through. Okay, here's the start. This is a histogram. This is a histogram created in R with the hist function. That's the normal hist function. What hist does is it draws this picture and it returns some information about the picture that it drew. That's why I'm assigning it over here. Hist. The BrailleR package. So there's a blind researcher, Jonathan Godfrey, who's created the BrailleR package. What that does is it takes that information about the histogram, the P, and it's got a function called VI that turns that into a set of text. Now, if you can't see this picture, you can't see the text either, but if you have a screen reader, then the screen reader will read out this description and you have some idea of what you just did. And the interesting thing about this that Jonathan pointed out to me is it's not so much trying to let people understand what's in this graph, it's more useful for them to know, what did I just draw? What do people who can see this thing see when I run that code? Okay, so that's not my work, that's Jonathan's work. So don't be impressed with that, my stuff's coming. Right, this is a ggplot2 histogram. So the other one was a base graphics one. You may, if you use R, you've probably heard of ggplot2. So lots of people would make their histogram this way, not the first way. So recently I had a student, in fact last year, Deborah Warren, who took BrailleR and added support for the ggplot2 stuff. And so now you can take the VI function, give it the ggplot2 object, this G thing, and it produces a text description, and if the screen reader can read that to you, then you have some idea of what you made with ggplot2. Also not my stuff, but getting closer, because I at least talked about this thing before Deborah actually did all the work. Now, getting closer still, when you draw these plots, sometimes there's color. Look, so this is a histogram with some color in it. Not very good color, I don't care. I'm interested in what the colors are, really. If you put that into this VI function, it produces a text description. And there's a little problem, which is that. So the screen reader reads out to you that you just created a histogram with F8766D in it, right? And I'm not blind, but that doesn't help me either, right? So there's this little piece of what Deborah did, which was really cool and very big. This little piece that sort of was left undone, or not as good as we could get it, maybe. So, my bit. This recent work was, of course, if there's a problem, you make an R package to solve it. So I've created a package called rolloc, not as somebody I was talking to thought R-olloc. It's color backwards, right? I didn't see that one coming, but all right, so the package is called rolloc, and it has a couple of functions. So there's a color name function, and you give it one of these specifications that doesn't tell you anything about the color, really, and it gives you back a name. Yeah. Okay. And there's this color swatch function that draws you a picture of the color specification you gave it and the color name, plus a little rectangle to show what those colors actually are. That's for me. That's just to check that it's doing something sensible. Right. We could be done at this point. That's the destination. But I don't think we have enough questions and answers to fill up the rest of the time. So I'm going to go now to how I got to this, which is sort of the more interesting part. Okay, so what are the problems involved in generating a package that takes color specifications and turns them into color names? Problem number one, which names? What color names do you use to choose from when you've got the color specifications? R actually has a large number of color names that it understands, 657 of them. The first 20 are there. So there is a list of color names sitting there available to me, so I could use that. But there are other color lists actually the one that R uses is used in a number of different places like cascading style sheets and HTML. But there are other ones. This is the list of the HTML list of simple colors. There's only 16 of them. And I guess one of the important things is that that color there, which this list calls lime, is green in the other one, right? So one of the problems is there's more than one list, and the lists don't agree. I promised XKCD, and I will deliver. So Randall Munro ran a web survey and on his webcomic site, and he got lots and lots of people to respond with what they thought a color was based on giving them visual colors and them naming them. And then he drew a map of the RGB color space and what people mostly thought these names corresponded to. So that's another list. You can actually access that, and you could map colors to those names. Thing is, there is no single obvious best one. Okay? So when I came to design the Rollock package, what I did was give up and let you decide, right? And this is my first piece of wisdom, which is that when you are writing code and you're struggling with something where there's a couple of options and you're feeling like if I make that decision, I'm really committing myself and everyone to that path, then don't do it. Give it, there's your function argument. Make it so that people can choose between the options. Particularly in this case, because there's actually more color lists that I haven't named and more color lists that I haven't discovered yet. So I want people to be able to plug in as they sort of figure things out. So this is actually using the color list that gives Maori color names for the color specifications. And hopefully it's getting it right. Okay, second problem when I'm developing this package. I have the color list, which is the list of color names that I might want to choose from. But the set of possible color specifications that there could be is actually much, much larger than the list of color names. So in those color specifications that look like this, there's 6 digits, and each digit can have 16 possible values. So there are nearly 17 million possible color specifications. R has a list of color names that's 657 colors long, which seems like quite a lot, but it's much less than 16 or 17 million, right? And if I had a list of color names that was 17 million color names long, I'd be surprised if I could understand it. Okay, so my next sort of problem is I'm going to have color specifications, much smaller list of color names. How do I map between the two? And I want to basically do something like say, right, which color name am I closest to with this color specification? So in this example here, down the left-hand side, I have color specifications that are slowly changing. And on the right-hand side, I'm going to have to use the same color name for different color specifications because there's just not enough of these. Plus, it doesn't actually matter that I call these two the same thing because they look like it to me. Right. Now the color space we're working in the color specifications, set of R, set of G, set of B, red, green, blue. That gives me a 3D color space. So red on one axis and green on another and blue on another, and there's all the colors that I could possibly specify. So the obvious thing to do would be, let's find my color specification in this color space, then let's put all the color names in there. So all the light colored things swirling around there are the color names on the 657 long list. And then I'll try and track it with the mouse, the bright red one down there that's a color specification, and I just sort of draw a straight line to all the other color names and choose the shortest one. That's something I could do. But this RGB color space is not the only color space. I can organize colors in different ways, and people do. This color space is called CIEXYZ, which is about as much as I know about it. I've sort of chosen this for two reasons. One, because of this, and I'd like to apologize for this slide because this is the most maths I've ever put on a slide ever. And I chose a public lecture to do it. The only reason it's there is to sort of demonstrate that there is a formula for going from RGB to XYZ. So any RGB that I have, I can get an XYZ for it, right? That's pretty much all I need to know about XYZ. And the other reason I want to know about XYZ is because I can use that to get to another color space, which is called CIELUV, which again is about all I'm going to tell you about it. But there's a different arrangement of the colors in this space. The advantage of this color space is that the colors are arranged so that if I go in a particular direction, a fixed amount, then perceptually, that's the same change in color. So let's assume my arms are the same length as each other, right? So if I go from here to there in this color space, and I go from here to there in this color space, that color seems about as different from that color as this color from that color, right? So that's the advantage of this guy. That's why it's all sort of warped-y compared to RGB. Now, that's quite useful if what I'm trying to do is measure color distances in order to figure out what's the closest color name to my color specification. It would make possibly more sense to measure distance in this space rather than RGB. Distance has more meaning here. Sorry. All this says is that there's a formula. So I can go from RGB to XYZ to LUV for any RGB. So I can do this if I want to. And again, what that means is, with the rollup package, I want to actually let people choose how they're going to measure distance. Because although LUV might be better than RGB, there are actually other color spaces that you could go to as well, and they might be even better, and there are actually other distance measures you could use rather than just a straight line. So I'm going to make that a parameter of this system. Right. Design. I have two main functions in this package. One that just gives you the name of the color based on a specification, and another one that draws a picture. Now they're basically doing the same thing. They're basically measuring distances and then figuring out which one's the closest and reporting that closest one somehow. So there's actually another function in that package that underlies both of those that does the actual what's the distance between this color specification and all the color names. So I can get all the straight lines in one hit. And these other functions are sitting on top of that. Another thing I realized once I started working with this problem is that some of these color names, so there's two color names in that list of 657, one's called red, one's called red 1, and these are the RGB values that correspond to those things, and those two RGB values are the same. So there's two color names for exactly the same color. So it's possible to ask this system which color is closest and get more than one answer back. To allow for that, there are actually two other functions in this package, color names with an S, and that actually returns more than, well, it's possible for it to return more than one match, basically. and color swatches, which will draw multiple matches for a single color specification. And these two, of course, are also built on top of color match. Now, it took a bit of playing with this problem and trying out different things to actually discover that these are the sort of parameters of this solution, that you have to allow for these sort of situations as well as just a single color match. So the second piece of wisdom about this is when you're writing software, it's quite easy to tell when you've got it wrong because you start lying to yourself. You start writing functions and they work for a certain set of cases, and then you try another case and it doesn't work as well as you think it should. And you have a choice. You can either sort of go, I didn't see that, or you go back to the functions you had written and you rip them to pieces and you write them again better, say with a common function underneath them that does a simple thing that then supports all of these other things. Now, if you use R and you're watching carefully, the difference between the color name function is that it returns a vector. Every specification you give it, it will give back one name, so it's just a character vector. The color name Z gives you a list, because every specification you give it could give you one or more values, one or more color names back. So it's a more complicated data structure. If you want to write nice functions, the function should return the same sort of answer every time, the same type of data structure. So that's a better design than having a single function that sometimes returns a vector, sometimes returns a list. So you keep going, and the reward is that when you do get it right, you can tell. And it's very satisfying once you've sort of got something designed the right way. Plus, it's easier to maintain. Right. That's sort of the first half. I built a tool, and I had to encounter some problems and resolve them in order to build that tool that was sort of hopefully a general tool that would sort of work in multiple different ways. And it's quite typical of how I tend to work. There's a small problem, and I over-engineer a solution that is very general and very beautiful in my eyes, and much more work than it deserves. Okay? But it's very satisfying to do the solutions that way. But all I've done at this point is sort of built that tool. I've sort of gone, there's a problem, here's something that would help to solve the problem. It's not solving it yet, though. So what I'm going to do now is look at the tool that I built and assess it. How well is it solving things? And so when I said that the ending will be disappointing, I lied. The middle is disappointing as well. Here's a set of oranges, color oranges from the BrailleR package. And this is one of the sort of challenging things that this package was ultimately designed to solve. If you're drawing a plot and there's a set of colors in the plot and those colors are on a scale, a continuum, then ideally the color names that you got back would give you that impression that it would sort of go from light to dark, something like that. That would be quite useful. How are we doing? Okay. So this is using the R color name list. And there's some problems here because if you closed your eyes and I said to you, there's Burley Wood 2 on the screen, I doubt that you could really sort of grasp what that color means. And there's a bunch of those in that list. I don't know if you remember back at the start, there's antique white is one of the colors, or Alice blue. What are these things? So I don't know where those names came from, but they're crazy. The other problem is that if you have a list and it's a list of color names and it's quite small, then you get no accuracy. So here's the bunch of oranges, and everything is Karaka to this thing. Right? It can't distinguish between colors that are close together, and that's not very useful. Okay, I still sleep at night because I enjoy making the tool, and I can blame everyone else for not using it properly. They chose the color list. I just let them. Okay, and for me at least, this is where the enjoyment of building software is. You build these tools, these general tools, because that's more enjoyable and more valuable than just building a unique solution. Nevertheless, I'm going to now try and build a unique solution for this case using my tool that will help us out. Right, so what we need to find is a list of color names that is understandable and will distinguish between colors. There is a system called ISCC NBS. I know NBS stands for the National Bureau of Standards, I think, and I can't remember the other bit. But this is the description of their color naming system. And I see words like standardized, broad, and understood by the whole public. And that sounds like what I want. So I'm going to attack this thing and see if I can get a list of color names and a color metric that works for this guy. Right, here's some just examples of how it's going. And the good news is that these are at least plain language colors. There's words like light and pale and blue, and I can understand those. Plus, these colors are actually, it's able to distinguish between those colors that are visually, especially on that projector, not that far apart to my eye. Okay, so I'm encouraged by this, even though you laughed at me. Right. Okay, problem. The ISCC NBS system is based on yet another color system, which is called Munsell. Now, this is my favorite color system to draw because it's pretty. It's nicely spaced, and so again, it's skewed like the LUV one, right? It's all sort of squished out and all that sort of stuff. But again, that's because arranging colors this way means that distances are equal in terms of perceived differences between colors. And this one, although I said that the CIE LUV one was perceptually sort of even, it's sort of a bit even. This one's much better. This one's really good. Okay, so this is actually a great system to work in, which is why these guys built on top of it. But it's trickier to work with. And I'll get to why that is in a second. Plus, this ISCC NBS system is actually blocks of the Munsell space. So each named color corresponds to a region in this space. That means that my metric of distance is a bit different. Because now I'm sort of like, well, it's the same color, it's the closest to the color in the region that it's in. That's it. So it's sort of, am I in a block or not? Different sort of metric. Just as well, I designed my package so that I could choose color metrics and that sort of stuff, right? Okay, so here's what I need to be able to do. I need to start from RGB. That's where the color specifications live. I need to go to XYZ. I can do that because that's just a formula. There's another color space I've got to go through, X, Y, Y. Y indeed. And that's another equation, fortunately, so that's all right, I can do that one. This one here, though, that's a tricky step. I'll explain that in a second, and then I can finally go across to where I want to go. So there's a bit of work to do there. Plus, I'm going to have to define this distance metric that sort of says yes or no. Yes, I'm in a block, or no, I'm not. I'm just a million miles away. All right. The reason the step from, well, the reason RGB to Munsell is hard is because there is no formula for that last step. This bit here. There's no formula for that. So I can't just calculate it. And that's because here I'm plotting all those Munsell colors in RGB space. And basically, hopefully what you can see there is it's nonlinear. These things are they're on all those nice, lovely planes of colors that were in Munsell. They're all over the place. So, you can do a mapping, but you've got to do interpolation and extrapolation within that space to sort of figure out how do I get from my RGB to something that's in Munsell. All right, how do I actually do this? There's a package called Color Science that will help me. There's a function RGB to XYZ that will do that formula that we saw. There's a function XYZ to XYY that will do the next step, no problem. So I can just get, instead of RGB values, I've got XYY values. There is also, for the hard step, there's a Python package called Color. And that will do this interpolation and extrapolation to figure out the mapping from XYY to Munsell. Now, that's Python code, not R code, and I'm trying to write an R package. But fortunately, there's another R package called Reticulate that will allow me to call Python from R. And so I load Reticulate, I load the Python package using Reticulate, and then I call the Python using Reticulate, and this is an example of a Munsell color. It's a red. That's what I know. Right. That's good. And for the last step, I go back to the Color Science package, and there's a couple of functions that let me go from a Munsell thing to an ISCC-MBS color name, which is that. Okay, so the wisdom from that little series there is a sort of a slightly complicated task there, getting from RGB to ISCC-MBS. Fortunately, you pull together all these bits and pieces that other people have written, put them together, and you can get your solution. And that sort of should always be your approach, or your first approach, to use things that other people have written rather than writing them yourself, partly because you're lazy, but also because if somebody else has written some stuff and put it out there, then that's probably been tested more than the code that you'd write yourself. So it's good fun to sort of pull other people's stuff together and recombine it and make something new. I enjoy that. Right. However, I enjoy that, but it's hard for me to share that pleasure with others. If I need to install Python on my machine, I use Linux, and if I need to install a Python package, that's not too much pain. But if I want to give my R package to other people, and that includes Windows users, then I am giving them a whole lot of pain. And I don't want to do that because then they won't use my stuff. So I'm worried about the fact that I could solve this problem, but I need to use Python. How do I get around that? What if I do all the calculations myself? I can run this code on my machine, So I could just, for every single RGB specification, figure out what the ISCC NBS color name is and store it and remember it. And then I don't have to do that calculation ever again, and neither does anyone who uses my package. So I'll do that. Now that's a lot of conversions, almost 17 million conversions, but computers are fast, aren't they? Yes, computers are fast, but in some cases still not fast enough. This is a graph of how long it takes to call this function, the Python function, from R 1,000 times. And it's only 4 seconds, which is pretty quick until you scale it up to 17 million, at which point it becomes a day. And that's quite a long time to wait. Especially when you're developing something and you're sort of trying to do a calculation and check, does it work? And you have to wait till tomorrow to find out. Right? So I'd like something a bit more performant than that. Fortunately, I teach people that computers these days have more than one core. And it's actually not that hard in R to harness all of the cores on your computer and run them at once rather than just using one. So there should be 769 students from the past in this room nodding away and going, yeah, I remember that. I did that in the exam. So if you can harness this sort of stuff, you can actually bring the time down enormously on this sort of thing. And so this was, I don't tend to hit too much computing problems in my graphics work. So I was very excited to hit one of these. And even more excited because I had access to some hardware and I was able to throw 60 cores at once at this problem and bring it right down. So I was able to sort of do this calculation within a reasonable time. Problem is, the next step, once I've got to Munsell, I've still got to get to the color names. And this step was even worse. Now, again, we've got times going up here and number of times I'm calling the function going along here. And this is 60,000 conversions, only taking, well, only 80 seconds. But the really dangerous thing about this graph is that it's curved, and it's curved up. So I've got to get from 60,000 to 17 million over there somewhere, and that curve's going to be really high. I waited quite a long time before I figured out that this wasn't going to end in my lifetime. So I need to bring this one down as well. And this is a bit of a problem when the growth is exponential. It's really going to kill you. Okay, turns out that the problem in this case was a different sort of a thing. Well, actually, the solution was different. So I also teach people that R code can be very inefficient if you don't write it properly. So can anyone tell me what's wrong with this piece of code? And it's not the for loop. The fact is, this bit here, within a for loop, it's modifying a data frame. And that's going to cause great inefficiency in R, especially if you do it lots and lots of times. Okay, so creating a data frame outside a loop and then inside the loop, modifying the data frame over and over and over is going to kill you, like that. Okay, so I had a look at the R code for this function. Why is it going so slowly? Because it's actually not that hard a calculation, this last step. Notice this inefficiency. The other thing I teach is, well, if you've got inefficient code, what do you do about it? And so one of the things you can do is, well, don't write loops. So I could write my own function that did the same transformation, just modifying the one that they had. And the line down the bottom here, this is my one. And there's two good things about that. One, it's much lower, so it's going much faster, and it's straight. So that actually just killed that problem straight away. And the important wisdom about that, or the thing I want to reflect on about that, is that I was able to do that because the code I was calling, the R package Color Science, that's an open source package, and so I could look at the code. It ran very slowly. Why is it running slowly? I looked at it. It's running slowly because it's stupid. I'll fix it. But I could do that, right? Apologies to the Color Science author. I just broadcast that around the world. I don't mean that. I was being flippant. Right. And the other thing about it is, when I made my changes, I don't have to just keep them to myself. I've put my changes to their package on a GitHub account so that they can track the differences between what they've got and what I've got, and they could even merge it together and that sort of thing. And so I could share my code back. Now, for people my age, it's important to reflect upon that sometimes because it seems very easy nowadays, but that's really cool that you can do that. And it makes your tummy warm. Okay, unfortunately, I've now done all the conversions, and I have the answer. And it's very large, at least very large in terms of an R package. So nearly 200 megabytes is a bit much to ask people to download just so that they can convert a color specification into a color name. It's a bit heavyweight. Cran would probably scream at me. So what am I going to do about that? Well, I figured out that I've done all these conversions and I've done them in order from the first RGB specification I could think of all the way down to the last one. So I don't actually need all those RGB specifications. I could just remember the names and keep those, and I know the order, and so I can figure out which one I need. I thought I was very clever. And another thing I teach is how does R store things in memory? And it turns out that if you've got something like that where you've got a character vector, essentially, a big set of names, and you store it as an R character vector, then you're only storing every unique name once. So the size of this thing, rather than being 200 megabytes, comes down to under 3. And that's small enough to put in a package, just. So now I have the answer to all of the conversions, and I can distribute that rather than asking people to install Python. And that's much friendlier. I like that. Okay, so we now have an ISCC NBS color list and a color metric. And so I can throw those oranges at it and get back color names. And here we have our final disappointment. But it's actually not too bad, I think. For example, we go from sort of things involving yellow to things involving orange, and I can sort of picture that in my head. I go from things involving pale and then light and then strong, vivid, deep, and I sort of see a bit of a transition in that. So actually, I feel like I might actually have some names that convey some of the information in that color scale, at least a little bit. So overall, there was, again, the journey was really cool. I started with a very small problem, and I hit it with a very large hammer. And it's not clear that that's enormously useful to anyone. But maybe that's just because they haven't started using it yet. But the process was very interesting. And that's partly why I enjoy my job, because it involves all of these things. Oh, and in terms of the usefulness, actually, Jonathan Godfrey, the guy who wrote BrailleR, right at the start, right? He actually emailed me this morning because he had been trying to decide on a color scheme for his kitchen. And he'd been given color names like anglaise and bone and thistle and another one that I can't quite remember. But these sorts of names that we've got from the R color list that are sort of like, well, that's lovely, but I mean, my house has got Kaimanawa, and I don't know what that is until I look at it again when I get home. And so what I was able to do was take these color names, convert them to color specifications, and use the package to convert them to simpler descriptions of what the colors are. And he seemed happy. So we're on the way. Right, so the BrailleR stuff was Jonathan Godfrey's, the ggplot2 stuff was Deborah Warren's, and my stuff was the Rollock bit. I want to end to sort of tie this back a little bit to why we're here. So what I've sort of described is this process of taking a problem and sort of solving it for itself to some extent, and trying to solve it properly, building the package so that it really works and it's flexible and it's designed well and that sort of stuff, right? And it doesn't necessarily solve a massive problem yet. So I want to acknowledge the fact that what Ross did with R has actually helped to create a bit of space for that sort of work to be allowed, because that's sort of what he did with R in the first place, and look what happened. And so all the rest of us can sort of go, doesn't do anything yet, but in 20 years' time, we'll have a lecture series named after me. What he also did, when they did the original work on R, they tried to get it right from the beginning. And that's really important, of course, in the case of R, because there's so much built on top of that now that if they just sort of cut corners at the beginning, things would be teetering and falling over. So again, as a role model, that was a really good thing to see as a PhD student, that sort of approach to doing this sort of work. And finally, all that openness stuff, the fact that it's completely, utterly normal now to do statistics research, write code that implements it, and give it to everyone in a way that anyone can access and reuse and modify and give back and build on and all that sort of stuff. The success of R, or the existence of R, has played a big role in that, in creating that community and that basically that norm for how we should do our work. And so I'd like to acknowledge that as well. And that's all I have to say about that. Thank you.
Oh, I beg your pardon. Paul, I was at your, the last talk I went to for yours was talking about how to publish work that you do along these lines. And I enjoyed that talk very much. And here you are doing the same thing. So how would you link your previous talk that I was at about 2 years ago about how to publish this kind of work and get credit for it in the research community?
Right, so so that talk was about how to publish without going through a journal. Let's summarize it like that. And so I guess that relates to, well, the bottom point really, I guess, the openness side of things. So critical to that is the fact that this openness relies on there being all sorts of technologies like Git and GitHub and before that Subversion and that sort of thing, so that sharing of these things, well, and before that, things like the internet, so that sharing things is utterly trivial. These are necessary conditions for this openness to occur. And another part of it is licensing. So the fact that there are frameworks like the GPL and like Creative Commons licenses that make it easy for people to create things and explicitly label them as you may do what you want with them. So having access to those sort of things, it works for writing documents as well as for writing code. I guess that was That was the point of the other talk. That you can apply a lot of the things that you do when you write code to writing documentation about code. You can version control it, you can share it, you can publish it by making it available through all of these tools just as easily. Everybody can be a publisher. You have an issue with credibility, but that can also be solved. Because people will yell at you if you're doing rubbish. So what? You put crowd in front of verbs now, right? Crowd criticism, crowd peer review. These things can. There's an environment now where there's a different way you can work. Does that answer?
So you jumped through some hoops rather than replicate the Python Munsell mapping function. Was that simply laziness, or was there something about that function that was particularly difficult to replicate in R? And more generally, are there things that Python is better suited to than R?
Okay, so I'm just trying to this guy, right? Okay, so you're going to ruin my story. There's a function like this in the color science package in R. Doesn't work. So I actually first found the code to do this in an Octave, which is a free version of MATLAB set of code. Couldn't get it to work. Found the R package, couldn't get it to work. Then found the Python one, and that one's got a large amount of support around it and seems to be maintained, and that worked. So that was why I went with that one. Second part is, yeah, it's not trivial, the iterative process that they're going through to do this search for what's the right Munsell color to match to. And that was one where it's like, writing my own version of the code, I don't want to go there unless I absolutely have to. Particularly because in this case, yeah, this Python project is big and established and so forth. So trying to do better than them is, or trying to do as well as them is probably wasted effort.
Before the ICC and the S whatever thing,
Yeah.
back when you have point colors, it seems that you might want to have bigger neighborhoods around sort of normal colors than around weird colors, so that if something was the same difference from red and, burnt sienna, that you'd call it red. Did you think of...
Have I got an answer for you? There's an argument in the color name function that says, which color metric would you like? And if you don't like mine, you're welcome to write your own. So, no, I haven't written it, but yes, you can.
So the metric...
The metric is given the set, the color specifications, and the color list names and specifications that correspond to them, and away you go. So you could transform to whatever color space you like, and you can do whatever metric you like.
It doesn't have to be a metric, it just has to be something that's smallest for the one you want.
You have to produce back a matrix of color specifications, color names, distances.
But the only property the distances have to have is that you want the smallest one.
That's the one that the other functions will pick. Yeah.
Yeah, because it won't be a metric in lots of other ways, but it will be good enough for what you're...
Yeah. I mean, you could do one so that it actually chooses the furthest color away if you wanted to. I'm not stopping you, right?
Paul, the names aren't particularly useful to somebody who's blind, right? So wouldn't it be more useful to actually present the Munsell values to them? Because that's systematic.
Well, I can't speak for blind people, so I talked to Jonathan, and he says, well, when we describe and gave examples of the Munsell colour system, he said, "Are you kidding me?" And when he emailed me this morning, he was happy. So, I mean, I'm a sample of 0, so a sample of 1 is better. And Jonathan has access to other people and students who you can test this stuff on. So yeah, I mean, there's yet to be established. And again, in this case, actually the ISCC NBS solution is just another one. I don't know how good it is. I actually created my own simple color list by just taking the LUV space and putting some names in a regular sort of grid around it with just normal sort of light, dark sort of thing. And it sort of works better to me. Part of the problem is that this color space, I mean, I've drawn it with gaps in it because so that you can sort of see the inside, right? It doesn't actually have that big gap in it. But it does actually have some gaps. Like if you start from RGB and try to go here, you miss sometimes. And that's quite a problem. So yeah. But I don't know what the best answer is yet, which of course is another good reason for building the tool rather than the answer.
So those of you who are familiar with this series will know that this is the part of the evening where we normally give the speaker a T-shirt. You might notice that the speaker is already wearing one, and by his own admission, he is a computer programmer. And so if he was an average computer programmer, I reckon that would be enough clothing to last him a month. But he's a really good computer programmer, so that'll be enough clothing to last him till next year. And those of you who know me well know that basically I'm a bit of a bastard. And one of the practices I've decided that I will adopt for this series is to follow the footsteps of the professional football teams, either rugby union or association football, and that I plan to change the strip every 2 years. So there will be a new design. Paul doesn't know this yet, but we promised to give him one of the new T-shirts next year. And if you can keep looking out for those. So at this point, can you please join me in thanking Paul for an excellent talk. As per last week, we have some T-shirts to award, and we're going to ask our esteemed speaker to draw the names. We have changed the rules slightly, so you do have to be present, and you have to be willing to stand up and come and collect your shirt. Those of you who are again watching from a distance, we haven't solved the problem of how to award you T-shirts, but we will fix that for next time.
There we go. Satnam Singh.
Go on, Satnam. We all know you. We've seen you loitering in the corridors.
I'll get them fitted after this, yeah.
Okay. So it's just a handshake, isn't it? Yeah. Congratulations. And here's your proof. How many are we doing? Three.
Yeah.
That's one. Simona. And I don't know what the surname is, although it could be Katutsi. Is that right? Congratulations.
Thank you.
You can take that.
Yeah, after for a shirt. Yeah.
Yeah.
Cool. One last one.
One last one. It is Amy Galvin.
Excellent.
Congratulations.
Thank you. Very lastly, again, as per last week, I must mention our campaign again. What I'd like to direct your attention to firstly is how high the total is already. And I want to give a personal shout out of thanks to those people who have been very generous and donated to this campaign. There is an opportunity for those of you who haven't donated to give, of course. And I know, once again, that there will be some R nerds in this room, or at least I'm fairly sure there are. And I have some of those little hex stickers that you all like to stick to your MacBook. So if you are willing to complete a small donation form, which Liza has, then we will give you one of these things. So again, thank you very much. Please join us again next week. We have a fantastic final speaker in Alberto Cairo, talking to us about data visualization in data journalism. And Thomas doesn't know this yet, but he might provide some spoilers for next year's series, which is almost organized. So thank you again, and see you next week.